Hi guys. Um, I know what you're thinking, and yes, I've been wearing the same shirt for weeks. Um, so today I want to talk about conservation laws. This leads into it's a different perspective on the way that nature organizes itself. Um, Forces of Newton's laws of motion, things like that, and that allowed us to describe the way that objects bounce around and roll on hills and do all sorts of things. Um, and that's a fine way to try to study nature. Um, but it's not the only way to try to do it. So today, I want to introduce just the general concept of something called a conservation law. And then we will use two different conservation laws to describe nature in different ways. They have their different uses. Some problems you want to use some momentum conservation, and other problems maybe you want to use energy conservation, and some problems you want to use both. So it's just a different way to approach problems. Okay. So the key idea of a conservation law is that you identify some quantity, some label, something, and um, and it needs to be something for which it's stable. It doesn't sort of vanish somehow. It seems to always be accounted for. And really, you just do the bookkeeping. So you're just accountants. That's all you really have to do. Um, so conservation, to conserve, means that something is not changing, is the idea. And then you're in physics, you're going to try to use to identify something that doesn't change and leverage that to solve a problem that would be hard to solve in any other method. Okay, rather than diving into physics, let's focus on stuff that's simpler. Okay, so to use conservation laws, you need to first identify what you want to study, and we call that the system. So we imagine that the universe, that's everything. That's way too much. We're kind of small, simple people. So let's focus on a subset of the universe. So I'm going to call the subset my system. These concepts should be familiar for most of you. You know, if you're taking chemistry, you use these ideas. All right. So I have the universe is everything. I have my system, and then I have excuse me. I have the environment. The environment represents the complement to the system inside the universe. So it's everything in the universe that's not in the system. Um, in physics, we use different kinds of systems. Um, so, closed system. A closed system is a system built out of a collection of masses, and those masses never leave the system. So it's just the group of masses. They don't even have to be at the same place. They just are all kind of considered one object. So you could imagine a mass here, a mass here, and I make them my system. I deal with their properties in total. Next semester, you'll also learn about something called a control volume system. And that's a system where you don't control, excuse me, you don't control the masses or limit or keep track of the masses individually. Instead, you keep track of what happens in a fixed region. You control the volume. So that's a control volume system. There are lots of ways to do this and different ways to apply these ideas. Okay, so you break the universe up into system and environment, and then you have some sort of quantity that you want to count. It's really just that. It's like counting marbles in a jar. So, um, so inside the system, there's some quantity. And presumably the environment has some bit of that same stuff as well. Okay, so maybe I shouldn't call it quantity. Let's just call it system. Inside the system has stuff in it. And the environment will have some stuff also. Okay? So both the system and the environment have stuff, but we are going to focus on the system. So we don't have to do all the bookkeeping to figure out how much stuff is in the environment. We just focus on the system. And so it could be a really boring problem where that's it. The system has stuff in it and stays the same forever. And then we would say stuff is conserved. So if the amount of stuff in the system doesn't change, and we say stuff is conserved. Okay. We say stuff is conserved. All that means is it doesn't change. It's just if we just say it was constant, that'd be too easy. Anyone can understand what we're talking about. So to jazz it up, we're going to say it's conserved. Good advice. Creates job security. It makes people think you know what you're talking about. Jargon. Okay, so that's the most boring sort of problem. The amount of stuff inside never changes. It's conserved. More typically, that isn't what happens. More typically, there are interactions between the system and the environment. And so the environment and the system can exchange bits of stuff. So we're going to call those interactions. Okay, so from this point of view, interactions are actions which allow stuff to flow in or out of the system. And typically, we choose minus signs so that if you add stuff, you're going to kind of count that as a plus sign, and stuff that leaves is going to count as a minus sign. Typically, you choose that sort of situation. But not always. When we get to thermodynamics next year and we have work, we talk about engines and things, we think about energy leaving the system in the form of work as being positive work, as opposed to energy coming into the engine as being positive work. So that's okay. Those are little details that'll change case by case. But the big picture is the same. So I'm going to redraw the same concept. But before we do that, let's talk about an example of how this might work. Bank account balance. Okay. The system could be your checking account, and the stuff inside could be the amount of money. So $100 is what you have in your bank account right now. Very good. So right now, so let's draw a box here. Let's draw our system, your bank, and right now you have $100. Okay? And then you go to the store and you interact with the store. So that means you put your debit card in, you type your code. That's your interaction. Okay, so your interaction, in that case, so let's think about that. When you interact with the store, then as you buy something, that represents there's going to be an outbound flow of money. So what we're going to have then is an outbound flow is your interaction as you spend money. Okay? So in that situation, the environment is the rest of the global economy, I suppose. So when you spend money, that's you interacting with the rest of the world, and the interaction is causing money to leave your system, namely your bank account. Okay, so let's add some numbers. So let's imagine that you start with $100. Let's imagine you start with $100, and then you spend $10. Okay, so you spend $10. Well, we all know what happens. After you spend $10, you're left with $90. Okay, so that was kind of before, and then you spend the money, and then afterwards, I guess this is before. After, you have $90. Okay, what's the relationship between all these numbers? Well, there's not one way to write it. Probably the most convenient way to write it, though, is to say the following. The change of money, the change of stuff, whatever it is, in your system, equals the flow out. So in this case, I would say, I could write that as saying $10. So I say the flow out is $10. And that equals, well, $10 equals, oh, let's be careful. Minus signs. If you're spending money, I want to say that the flow out is a negative 10. I apologize. I should have caught that. It's a negative 10. So my flow out, right today, apologize, is $10. Very good. So if the flow out is $10, and I want to connect that to these numbers, I say, oh, well, that's just the final balance minus the initial balance. And that's right. So we're going to say the flow out equals the change inside. And in this case, the flow out would be $90 minus $100. Okay? So as you spend money, you can relate the flow out not with the amount of money in your account, but with the change in the amount of money in your account. So if you spend, if you see somebody walking down the street and you see them spend $100, then you don't know their actual bank account level. All you know is the change in the bank account level. So it's really important to understand that the flow out doesn't tell you what's inside, it only tells you the change in the inside. You're going to see this concept over and over and over. In fact, this is quite literally, I don't know, 3/4 of thermodynamics. So if you understand this, and it's this, it really is this easy, even there it's this easy, it's just, it gets sort of hidden underneath lots of jargon. It really is this simple. So be sure to realize that the flow out is related to the change inside for this problem. Now, you could also have flows into the system. Well, that's easy to handle. If someone were to add money to your bank account balance, you get paid or whatever, that represents a gain of money for you or a gain of stuff. And you would have a flow in, and that's going to cause a positive change to your bank account. So what we really want to do to generalize this for all possible situations is to think about the following situation. I'm going to kind of borrow notation or the way that I do this with my understanding physics class. And we're going to imagine we have our system. And you have stuff on the inside. So in this case, it could be your bank. So that could be the bank. So we'll just make that the bank. And you have money on the inside. And there are all sorts of interactions you can have. You could have inputs or deposits. And you could have withdrawals or losses. And then the bank account will have changes. This will be the change in the account. And the general relationship is going to be the following. The total, or we're going to say that the inputs or the deposits minus the losses equals the change inside. Okay, and that's really the way to think about conservation laws. It's really no different than simple accounting. That every time you add some money, the bank account level rises. Every time you spend money, the bank account balance lowers. And the net interaction, that's how we're going to phrase it, the net amount that you add minus what you take out tells you what happens on the inside of your bank account. So it's really that simple. You can do the same thing. You wouldn't have to do money. So I'm recording this before a lot of the flu starts to spread around Jamestown. So right now, I went to the grocery store the other day and there was no toilet paper for sale. So you could do the same exact thing. So you could be at home and you could be studying your system could be your house, your toilet paper supply. And so this could be your home. And what you would have is, these are the number of rolls you buy. On the other hand, this could be the number of rolls you use. And then that's going to tell you the change in the number of rolls in your house. Okay, so you can use it. It's just a simple way of doing bookkeeping, really. It's just accounting. And conservation laws are really conceptually no more complicated than input, output. It's simple. Input, output gives you determines the change on the inside of something. Okay, so next up, we're going to apply this basic kind of, I don't know, it's kind of first grade level way of thinking, but we're going to apply it to a physics problem, or several physics problems. We're going to introduce the concept of momentum, and the momentum will be something which could be conserved, and we will have we'll talk about what happens as an object moves around, and if it interacts with its environment, the amount of momentum inside it can change, and we can basically follow all of these same kind of concepts. So you have a system and momentum on the inside, and interactions with the rest of the environment. We will call those impulses, and but you do the bookkeeping in much the same way. Okay, thanks. See you guys next time.